Your body is made of atoms. But atoms don't act randomly. They follow a code, a precise mathematical language, hidden yet universal. What if the universe isn't just built, but programmed? They told us atoms were simple, tiny building blocks orbiting like miniature solar systems. But what they didn't tell us was that atoms don't think. They don't guess. They don't improvise. They follow rules, unseen, unspoken, and, until recently, unimagined. Every movement of an electron, every shape of a molecule, every drop of water and breath of air flows from a silent mathematical code. A code that operates behind the scenes of all matter, guiding atoms not with force but with permission. A code that doesn't ask what can happen, but dictates what must. You are made of atoms, but your atoms are not made of randomness. They are made of obedience, and in that obedience lies the blueprint of reality. In the beginning, science saw atoms as solid, indivisible beads, Democritus's ancient dream of an elemental foundation. But even then, the mystery lingered. Why did some elements burn bright while others sat still? Why did iron pull and gold gleam? Why did matter in all its forms behave with such stubborn consistency? The answer was waiting, buried not in the atom structure, but in its law. Zoom in far enough and you'll find not chaos, but constraint. Not wild energy, but strict choreography. The universe does not improvise, it composes. Like music with only certain notes allowed, atoms form symphonies within bounds, following rules they cannot break. Rules we didn't write, but are written into everything we are. This is not metaphor, it's not poetry, it's physics. Electrons do not orbit freely. They can only exist at certain energy levels, discrete, precise, and immutable. These aren't distances, they are solutions to equations buried in the heart of quantum mechanics. Like pre-programmed inputs, electrons snap into positions defined by a set of numbers, quantum numbers, each one a variable in a vast, invisible algorithm. This algorithm isn't optional, it's absolute, and yet it's hidden. You cannot touch a quantum number. You cannot peel it from an atom like a label. But if it were not there, the atom would fall apart. Matter would dissolve. Chemistry would vanish. Life would never begin. Each electron is assigned 4 quantum numbers, like a 4-digit password that determines where it can exist, how it can behave, and whether it can even be. These are not identifiers. They are constraints. They do not say what is, but what is allowed. Imagine a world where a house could only be built on coordinates ending in prime numbers. A world where every doorway required a unique sequence of steps to unlock. That world is the atom. That code is its law. But who enforces the law? No one. And that is the terror, the beauty, the awe. There is no architect standing over every proton telling it how to behave. The rules are not enforced, they are embodied. Atoms don't choose to follow the code, they are the code. And that's where our story begins. It begins not in the visible, where atoms form steel beams and glassy oceans, but in the invisible logic beneath, a logic older than stars, a logic so rigid it cannot be negotiated, and so elegant it can build everything you've ever touched. The story of this hidden code takes us through the quantum numbers, the abstract values that define an electron's place in the atomic hierarchy. We'll see how this structure organizes the periodic table like a puzzle already solved, how it shapes the bonds between molecules, and how ultimately it determines the chemistry of life itself.
But first we must let go of the familiar.
Because the atom you think you know never existed. The Bohr model, those neat planetary rings with electrons zipping around like cosmic marbles, is a lie of convenience, a placeholder for something far stranger. In truth, electrons do not orbit. They exist in clouds of probability, zones where their presence is not certain, only probable. They don't travel, they appear, they aren't there until you look. And yet, they still follow the code. Even without being real in the way we understand it, electrons still obey. They still fit into specific slots, defined not by force or shape, but by numbers. The first quantum number, the principal number, defines the energy level, how far from the nucleus the electron can exist. The second, the angular momentum number, determines the shape of its orbital cloud. The third, the magnetic number, gives orientation. And the fourth, the infamous spin, defines its intrinsic angular momentum, even though the electron itself doesn't physically spin at all. Each of these numbers is a rule, not a suggestion, not a range, but a lock, and the locks only open in very specific, very limited combinations. No two electrons in the same atom can share the same four numbers. That's the Pauli exclusion principle, a rule so powerful it literally shapes the size of the universe. Without it, matter would collapse, stars would implode, everything would fall into itself, indistinct and indistinguishable. So the electron obeys, not because it must, but because it has no choice. And here's where it turns eerie. This code, this abstract pattern of allowed values, exists everywhere. In every hydrogen atom in the furthest galaxy, in every carbon atom in your breath. It doesn't vary by location or age or speed. It is universal. The same numbers, the same rules, across the infinite stretch of space and time. How? How did the universe decide on these rules, and only these? Why do electrons always fall into orbitals labeled 1s, 2p, 3d, and never say 5q or 7r? Why is the code so precise and so complete? No errors, no exceptions, just obedience. Some physicists call this elegance, some call it inevitability, others call it design. We don't know, but what we do know is that this hidden code, these quantum rules, do more than govern atoms. They shape reality itself. They are the reason hydrogen and oxygen bond to make water, why sodium explodes in contact with air, why gold reflects light the way it does. They are the blueprint of the periodic table, the skeleton of chemistry, the fingerprint of matter, and they raise a deeper question. If matter must obey these rules, does anything ever truly choose? Next, we'll explore what happens when these numbers collide, when two electrons attempt to share a state that isn't allowed, and how that simple restriction might be the most important rule in the universe. Because without it, nothing would ever be separate, and nothing would ever be you. You've seen the image in every textbook, a dense nucleus at the center, electrons whirling around it in perfect planetary rings, orbiting like miniature worlds, orderly, predictable, almost comforting. But it's wrong. This image, the Bohr atom, was a stepping stone, a simplification, a desperate attempt to make the strange behavior of atoms seem familiar. But in truth, atoms are not tiny solar systems. And electrons are not obedient moons, they are something far stranger. Strip away the illusion, and what you find is not structure, but probability. Electrons do not orbit, they flicker, they blur. They exist in clouds, smeared out across space, not in a single place, but in all permitted places at once. They are not where they are, until you look. And even then, the act of looking changes what you find. This is the quantum atom, and it is not intuitive, it is not visual, it is not human, but it is real. Let's begin at the center. The nucleus, that dense knot of protons and neutrons, holds almost all of the atom's mass. If the atom were the size of a football stadium, the nucleus would be a marble at midfield. And yet this marble contains nearly everything. The electrons, they're ghosts, massless wraiths compared to the compact fury at the core. But despite their insubstantial nature, electrons rule chemistry. They form bonds. They shape reactions. They are the social glue of matter. And they do so not with strength, but with rules. Rules that define where they can be and where they cannot. And this is where things turn peculiar. An electron cannot simply drift anywhere around the nucleus. It must occupy a very specific orbital. But these orbitals are not paths. They are probability clouds, regions where the electron is likely to be found. Imagine a swarm of fireflies blinking in and out of existence, never quite in one spot, but forming a pattern over time. This pattern isn't random, it's calculated. Each orbital has a shape, a volume, a character. Some are spherical, like bubbles. Others are lobed, like clover leaves. Still others twist into exotic forms with rings and nodes, but they are all determined, every curve, every shadow, by equations. The Schrödinger equation, to be precise. This is where the code begins to speak. The quantum numbers, those strange integers introduced in Part 1, are not just labels, they are solutions. Each valid set of numbers solves the equation for a given electron in a given atom, and each solution defines an orbital, its energy, its shape, its orientation, and its spin. But these solutions are finite. Not every arrangement is allowed. Not every number works. The code is exclusive, selective, structured, and that structure is what makes matter matter. Consider this. If you try to add an electron to an orbital that already holds one with the same spin, the code rejects it. No two electrons can share all four quantum numbers. That's the Pauli exclusion principle, a rule not of force but of impossibility, the quantum version of occupied. This one constraint reshapes everything. Without it, electrons would collapse into the lowest energy state. Atoms would shrink to impossibly small points. Chemistry, and therefore biology, would become impossible. You wouldn't just lose molecules, you'd lose complexity. So the exclusion principle is not just a limit. It's a gift. It's the reason the universe isn't one dense, collapsed singularity. It's the reason there's room for atoms, for stars, for thought. But how strange that all of this, the entirety of the chemical world, emerges from invisible numbers inside invisible particles. That every element, every compound, every breath of life begins not with a substance, but with structure. Let's take a step back. Imagine two atoms, one of hydrogen, one of helium. Hydrogen has one proton and one electron. Its lone electron occupies the simplest possible orbital, 1s, a small spherical cloud close to the nucleus. That's all it gets, nothing more. Helium, on the other hand, has two protons and two electrons. Its two electrons both fit into that 1s orbital, but only because they have opposite spins. That's the only way the code permits two electrons in the same space. Add a third electron, and suddenly it can't go there. The first orbital is full. The exclusion principle locks the door. So the third electron, in a lithium atom, must go to the next available orbital, 2s. It's farther from the nucleus, higher in energy, less stable, but it's available. This cascading arrangement, one shell filling, the next opening, creates the structure of the periodic table, the pattern of element behavior, the predictability of chemical bonds, all of it downstream from invisible quantum numbers. Atoms are not just particles, they are layered codes. Each layer, each shell, each orbital, a response to a limit, a workaround for a rule. The atom is not a machine, it's a negotiation. And somehow, across billions of atoms, trillions of molecules, this negotiation leads to water, to DNA, to fire, to thought. But let's not romanticize. The atom is not your friend, it is not compassionate, it is not curious, it is cold, mathematical, and absolute. It allows certain behaviors, forbids others, and everything in everything that exists survives within that permitted range. This raises a chilling question. Are we the product of creativity or of constraint? Do we exist because the universe is fertile and generous, or because it is ruthlessly specific? Are atoms building what's possible, or simply what's allowed? What's most haunting is how stable the code is. Across time, across galaxies, across conditions, these same rules apply. There is no known region where an electron is allowed to share quantum numbers, no variation in spin constraints, no deviation in the orbital shapes. The code doesn't flex, and yet it gives rise to the most flexible thing in existence, life. In the next part of our journey, we'll go deeper into the quantum numbers themselves, not just what they mean, but how they emerge. how these abstract numbers define everything from gold's glow to oxygen's reactivity, and how they may be the closest thing we've found to a cosmic source code. Because if electrons are ghosts, then quantum numbers are the rituals that summon them into form. And no one, not even the atom itself, gets to break the ritual. If you could look into an atom and see its rules written out like code, what would it say? It wouldn't be English, or Latin, or mathematics as we know it. It would be a sequence, 4 characters long, 4 values, precise and indivisible, together forming a kind of molecular passport. These are the quantum numbers, the hidden variables that tell each electron not just where it can exist, but if it can exist at all. Every electron in your body carries these numbers. They are not painted on, they are not chosen. They emerge as part of the electron's very existence, as natural and necessary as its charge or mass. And they must be unique. That's the catch. No 2 electrons in the same atom may have an identical set. This isn't superstition, it's law. The Pauli exclusion principle, introduced in the last chapter, doesn't just restrict behavior, it defines identity. The quantum numbers are how the universe keeps electrons apart, not by distance, not by color, but by code. Let's examine these 4 numbers. They are, in order, N, L, ML, and Ms. They sound like variables from an ancient equation, and in a way they are. They are the fundamental inputs to the atom's configuration, the source code of chemistry, and together they describe a kind of multi-dimensional address for each electron, N. The principal quantum number. This is the most familiar and the easiest to grasp. The principal quantum number, N, describes the electron's energy level. Think of it as the electron's shell, how far, on average, it is from the nucleus. It can be any positive integer, 1, 2, 3, and so on, but this number isn't just a label for distance. It defines the size of the electron's orbital, the radius of its probability cloud. Electrons in higher N levels are less tightly bound, more energetic and more reactive. Hydrogen's 1 electron sits in N equals 1. Oxygen's outer electrons occupy N equals 2. Gold, with its heavy mass, has electrons in shells all the way up to N equals 7, Shak 6. The higher the number, the more complex the behavior, yet N is just the start. L, the azimuthal, or angular momentum, quantum number. Once you know the energy level, you can determine the shape of the orbital, the form that the electron cloud takes. That's what L tells us. For each N, L can be any integer from 0 up to N minus 1. These values correspond to the familiar s, p, d, and f orbitals. L equals 0 arrow s, spherical. L equals 1 arrow p, dumbbell-shaped. L equals 2 to d, cloverleaf. L equals 3 arrow f, complex, diffuse. These aren't just decorative shapes, they determine how atoms bond, how molecules bend, how light is absorbed and reflected. L gives the atom its personality, defining whether it is inert, reactive, magnetic, or even fluorescent. The periodic table, that orderly display of elemental behavior, is built entirely on these shapes. Every trend, atomic size, ionization energy, electronegativity, emerges from how L and N interact. And still, the code continues. ML, the magnetic quantum number. Now that the orbital shape is known, ML describes its orientation in space. It tells you which way the orbital points. For a given L, ML ranges from negative L to positive L, including 0. For example, if L equals 1, AP orbital, ML can be negative 1, 0, or positive 1, 3 different directions for the same dumbbell shape. These correspond to the px, py, and pz orbitals in Cartesian space. These orientations aren't just academic. They determine how atoms interact with magnetic fields. They define the geometry of molecular bonds, the shape of a water molecule, the chirality of sugars, the folding of proteins, all depend on the invisible directions allowed by ML. And finally, the strangest number of all.
Ms, the spin quantum number.
This one defies our senses. Image can only be one of two values, plus 1/2 or minus 1/2. That's it. Two possibilities, no in-between. It's called spin, but this is a lie of language. Electrons do not spin in space, they are point particles. Spin is not motion, it is intrinsic, a built-in binary property. It is as if every electron is born with a coin flip encoded in its being. And yet this coin flip matters enormously. Only two electrons can share an orbital, and only if they have opposite spins. That's the loophole. That's how helium fits two electrons into the same 1s shell. It's also why lithium must move on to a higher shell, because no two electrons can occupy the same N, L, Ml, and Ms, not ever. So spin is the final key in this four-part lock, the last digit in nature's password. Let's pause. Why does this matter? Because this tiny set of constraints, just 4 numbers per electron, builds everything. Every element, every molecule, every cell in your body. When you burn magnesium, smell sulfur, or breathe oxygen, you're witnessing the outcomes of these numbers. When hydrogen fuses in the heart of the sun, when uranium decays, when fluorine tears electrons from other atoms, it is this code, these numbers, that make it possible. But there's something even stranger. We didn't invent these numbers, we discovered them. They are not arbitrary. They emerge from solving the Schrödinger equation, the fundamental wave equation of quantum mechanics. They are the only valid solutions. The code isn't something nature chose. It is something nature is. And it's eerily efficient. There is no redundancy, no waste. Every quantum number has a job. Every limit serves a purpose. The structure is compact, recursive, and universal. You could imagine a universe with different rules, with more quantum numbers or fewer, with electrons that could share orbitals or none at all. But that's not the universe we live in. We live in one where identity is defined by exclusivity, where complexity arises from constraint, where structure emerges from the most minimal set of instructions. It is, in every sense, a programming language.
And you, your brain, your blood, your bones, are running its code.
But the real question is, where does this code lead? In the next part, we'll explore the dark side of constraint. What happens when electrons try to occupy the same state? And how the universe enforces obedience by simply not allowing existence at all. Because the code isn't just elegant, it's ruthless. There is a quiet violence in the heart of every atom, not of motion, not of heat, but of denial, a force that doesn't push or pull, but forbids. A rule so absolute, so unyielding that entire stars hold their breath in obedience. It's called the Pauli exclusion principle. And it is, perhaps, the most important law in the known universe. Why? Because it says no, not softly, not reluctantly, but universally. No two electrons, within a single atom, may share the same set of quantum numbers. Not N, not L, not Ml, not Ms. If one electron is already in that state, the next one is blocked, not repelled, not relocated, blocked from existing in that configuration at all. It is not a physical clash, it is a logical one. And that's what makes it so haunting. The Pauli exclusion principle doesn't operate through space. You can't measure it with a ruler or detect it with a sensor. It is not about force, it is about permission, or rather, the absence of it. The forbidden state is simply not part of reality.
But this quiet lock and this invisible denial is the very reason the universe doesn't collapse into itself.
Let's run a thought experiment. Imagine for a moment that the Pauli principle didn't exist, that electrons could pile into the lowest energy state, all of them. Not just 2 in the first orbital, but dozens, hundreds, millions. The result? Atoms would shrink, not slightly, but catastrophically. Without exclusion, there's no reason for electrons to inhabit higher orbitals. They would all sink to the bottom, like stones falling into a bottomless well. The shells and subshells would vanish. The periodic table would vanish. Matter would become impossibly dense, unimaginably small, and identical. Because without exclusion, there's no way to distinguish one electron from another, No difference, no personality, no complexity, just uniform collapse. And you wouldn't exist. Neither would stars, or planets, or chemical bonds, or time as you know it. Now flip the scenario. What if you press the principle to its extreme? Welcome to the heart of a dying star. As a massive star runs out of fuel, it begins to collapse under its own gravity. The outer layers explode in a supernova, and the core, stripped of its fire, begins to compress. Down, down, down. But there is a limit. Electrons, bound by Pauli's law, refuse to be squeezed into the same state. The closer the particles are forced, the more they resist, not through force, but through degeneracy pressure. A pressure born not from energy, but from identity. This is how white dwarfs form. Earth-sized cores made almost entirely of electrons and nuclei, locked into place by the exclusion principle. They shine not because they burn, but because they refuse to collapse. And when even that fails, and when the star is so massive that electrons are crushed into protons forming neutrons, the exclusion principle comes again, this time protecting neutrons. Another lock, another denial. And so, neutron stars are born, city-sized orbs of unimaginable density, held apart only by the sheer refusal of particles to become identical. The Pauli exclusion principle prevents gravitational oblivion. It holds up stars. It holds up you. Let's return to the atom. In helium, 2 electrons fill the 1s orbital, opposite spins, locked in unique configurations. Try to add a third, and the code bars the door. No exceptions. The third electron must go higher, to 2s. This simple act, this restriction, ripples outward. Because the third electron is farther from the nucleus, it's less tightly bound. It can interact, it can bond, it can share. That's chemistry. All of chemistry, the behavior of elements, the formation of molecules, emerges from the inability of electrons to occupy the same state. Bonding isn't about closeness. It's about finding new configurations that don't break the rules. Think of atoms as puzzle pieces, not of shape, but of code. Bonding is about finding partners whose electrons can coexist without duplication. Every molecule is a compromise, a delicate arrangement of permissions. You don't form water because oxygen wants to. You form it because 2 hydrogens fit perfectly into oxygen's available quantum states, without repetition. The atom is constantly negotiating the exclusion principle. And what happens when the negotiation fails? Instability. Certain electron configurations are so constrained, so energetically unfavorable, that the atom becomes radioactive. It seeks a new configuration, a lower energy, a more obedient form. It does this through decay, ejecting particles, changing identities, rearranging itself until it can fit within the code again. Even decay, even death, is obedience. We often speak of the laws of physics as things that govern behavior, but Pauli's law is different. It doesn't just govern action, it prevents being. It makes certain versions of reality impossible. That is profound and disturbing, because it suggests that identity itself, your identity, the structure of your brain, the pathways of your thoughts, may be built not by expression, but by exclusion. You are not what can be, but what remains after all forbidden configurations are eliminated. This is not philosophy, it is physics, it is the code, and it raises a strange question, not of science but of symmetry. Why are there 4 quantum numbers? Why those numbers? Why this exact arrangement of rules that define what can and cannot exist? The Pauli exclusion principle doesn't explain why these numbers matter. It only tells us what happens if they are violated. But the structure itself, the quantum numbers, their interactions, their limits, remains a mystery. A logic without a legislator, a code without a coder. Next, we'll explore how these numbers, especially n and l, form the electron shells and subshells that define the periodic table. We'll see how the universe uses exclusion to build complexity, how atoms are forced into shape by the same rule that forbids collapse. Because when you zoom out far enough, you see something extraordinary. The entire table of elements is just the long, unfolding consequence of no. There is a strange kind of poetry in the periodic table. It looks simple, rows and columns grouped by color and abbreviation, but beneath its quiet grid lies something profound. The shape of the quantum code, unrolling itself into matter. Each row is not just an increase in atomic number, it is an unfolding of allowed quantum states. Every new element is a new electron, and every new electron is forced by the Pauli exclusion principle to find a unique configuration, a unique set of quantum numbers, a new way to fit. And this is what gives the periodic table its shape. Not preference, not chemistry, but constraint. Let's look closer. The first row contains only two elements, hydrogen and helium. That's not arbitrary. It reflects the limits of the first shell, n equals 1. This shell only allows one type of orbital, the 1s spherical. Simple. It can hold only two electrons, one spin up, one spin down. Once that space is filled, the next electron has no choice. It must move out. Enter n equals 2. This second shell introduces new orbital types. The 2s, still spherical, and the 2p, dumbbell-shaped, spread across 3 spatial orientations. Altogether, the second shell can hold 8 electrons, 2 in 2s, 6 in 2p. And with that expansion, the second row of the periodic table is born, 8 elements, from lithium to neon. But this isn't just a tally. Each shell, each orbital brings with it new behaviors, new chemistry, new reactivity. That's why elements in the same column behave similarly. They have similar valence electron configurations. The outermost shell, sodium and potassium explode in water. Fluorine and chlorine steal electrons with ferocity. Noble gases sit inert, aloof, their shells full. This isn't personality, it's geometry. Because electrons don't just exist in orbitals, they arrange themselves in layers, shells, subshells, configurations that dictate how atoms bond, how they repel, how they fit together. This is quantum architecture. And the architect is the code. Let's take a step back and watch the structure unfold. We begin with hydrogen, 1s1, a single proton, a single electron. The electron drops into the lowest possible energy level, the 1s orbital. Helium, 1s squared. The 1s shell is now full, 2 electrons, opposite spins. Next is lithium, 1s squared, 2s1. The first shell is complete, so the third electron must rise into the next shell. It occupies the 2s orbital, farther from the nucleus, higher energy, less stable, more reactive. Then comes beryllium, 1s squared, 2s squared. Then boron, 1s squared, 2s squared, 2p1. Now we're spilling into the 2p subshell, 3 orbitals, each of which can hold 2 electrons, giving us space for 6 more elements. Carbon, 1s squared, 2s squared, 2p squared. Nitrogen, 2p to the power of 3. Oxygen, 2p to the 4th power. Fluorine, 2p to the 5th power. Neon, 2p to the 6th power. At this point, the 2p subshell is full. The second shell, n equals 2, has reached its capacity, 8 electrons total, and so the third shell opens. 1s squared, 2s squared, 2p to the 6th, 3s to the 1st. The next electron goes into a new layer, more diffuse, higher energy, and the pattern repeats. But something strange begins to happen as we move to higher atomic numbers. The order in which orbitals fill is no longer strictly sequential. Sometimes a 4s orbital will fill before a 3d. Sometimes electrons enter 5s before 4d. Why? Because energy levels overlap. The spacing between orbitals becomes compressed. The code must now balance not only uniqueness, but efficiency, filling orbitals in the lowest energy configuration that doesn't violate Pauli. This creates patterns and exceptions. It creates transition metals with partially filled d orbitals. It creates elements like chromium and copper, where electrons shift orbitals to achieve more stable configurations. It creates the block structure of the periodic table, the S block, P block, D block, and F block, each one a reflection of orbital types. What looks like a table is, in truth, a multi-dimensional unfolding of quantum mechanics. Each column is a family, each row a new energy level, each block a new class of orbital, and all of it arises from exclusion, from the refusal of the universe to allow duplication. But this structure is not just academic, it is practical, because chemistry, as we experience it, is determined almost entirely by valence electrons, the electrons in the outermost shell. These electrons are the only ones available for bonding. The inner shells are too tightly held, too deep in the atom's well. So the shape of the periodic table reflects how atoms interact, how they form molecules, how they build reality. Hydrogen, with one valence electron, seeks a partner. It wants to fill its 1s shell. Oxygen, with 6 valence electrons, wants 2 more. It forms 2 bonds. With 4 valence electrons, it sits at the perfect midpoint, not greedy, not stingy. Carbon can bond in 4 directions, forming chains, rings, branches, lattices. Life is made of carbon because carbon is, quite literally, open-ended. And all of this structure, this behavior, this possibility emerges from quantum shells, from the allowed configurations of electrons, from a handful of numbers playing out across scale. This is why the periodic table is not just a list. It's a map of permission, of structure, of possibility. It shows us where the code says yes and where it says no. It is one of the only places in science where you can see the rules, etched into metal, printed on classroom walls, hung in laboratories. The table is a window into the code, not because we imposed it, but because we discovered it. And this should give us pause. How strange that matter is not a gradient, but a staircase, that electrons don't drift between states, they leap, that there are no half elements, no in-betweens, only allowed or forbidden. This is the quantum world. It does not blur, it jumps, it quantizes, it steps. And those steps, those discrete shells, shaped by quantum numbers, are the rhythm to which chemistry dances. In the next part of our journey, we'll explore something even more abstract, symmetry, not just as a visual pattern, but as a fundamental property of nature, one that shapes not only atoms, but the very laws of physics themselves. Because if quantum numbers are the syntax of the code, then symmetry is its poetry. Somewhere between order and freedom lies symmetry, the quiet heartbeat of the universe. You can see it in a snowflake, in the spiral arms of galaxies, in the wings of a butterfly or the crystalline lattice of salt. We often call symmetry beautiful, as if it were an aesthetic flourish. But in physics, symmetry is not decoration, it is commandment. Symmetry tells particles how to behave, it dictates the laws of conservation. It whispers, silently and universally, which moves are allowed and which must never happen. And like the quantum numbers, symmetry is not something imposed on nature, it is nature. Let's begin with the simplest idea. Symmetry means that something stays the same even when you change how you look at it. Spin a perfect sphere. It looks the same from every angle. Mirror a butterfly's wings. Left and right reflect each other. These are spatial symmetries, visual, geometric, and intuitive. But nature's symmetry runs deeper than visuals. What if you perform an experiment here on Earth, and then perform the same experiment on the Moon? If the result is the same, we say the laws of physics are translationally symmetric. They don't care where you are. Now imagine you do the same experiment tomorrow. Same outcome? Then time itself has symmetry. The laws don't change as the clock ticks forward. And what if you rotate your setup or flip it left to right? Still the same. Symmetry. But here's where it turns strange and profound. In the early 20th century, the brilliant mathematician Nother proved a theorem that shattered physics wide open. every symmetry in nature corresponds to a conservation law. It's one of the most beautiful and haunting ideas ever discovered. If the laws of physics are the same over time, then energy is conserved. If they're the same in all directions, then angular momentum is conserved. If they're the same in every place, then linear momentum is conserved. These aren't coincidences. They are mathematical consequences. Symmetry doesn't just suggest what the laws should be, it creates them. And this matters because atoms are not isolated particles. They are governed by these same symmetries. Their orbitals, their shapes, their allowed energies, all emerge from the need to respect these invisible rules. Let's go back to the hydrogen atom, the simplest atom in the universe. One proton, one electron. Its solutions to the Schrödinger equation, the orbitals, emerge directly from the symmetries of space.
The spherical 1s orbital?
That's because space is isotropic, the same in all directions. Hydrogen's s orbital reflects the symmetry of the void itself. The p orbitals, the d orbitals, they're not arbitrary shapes. They arise from how angular momentum behaves under spatial rotation. That's symmetry manifesting as geometry. The mathematics of turning something around and getting the same result. Every quantum number, n, l, m, l, m, s, reflects a symmetry being respected. N is tied to the radial symmetry, how energy changes with distance from the nucleus. L emerges from rotational symmetry, how angular momentum behaves. Milli tracks magnetic orientation, how orbitals respond to direction in space. And Ms, spin, that emerges from an even deeper, stranger symmetry, one that doesn't exist in classical space at all. Spin is a relic of relativistic quantum mechanics. It requires a special kind of symmetry called SU2, a group so abstract it doesn't map to anything we experience, and yet it governs magnetism, bonding, and even the structure of stars. How can something so unreal be so powerful? Because the universe is not built from shapes. It is built from invariances, from things that stay the same, no matter what you do, where you go, or how you turn your head. And atoms, in all their chaos, are anchored to these invariances. Let's take another example. The conservation of electric charge. Why do protons always have +1 charge and electrons always -1? Why do reactions never create or destroy charge but only shuffle it? Because charge conservation stems from a symmetry, a kind of rotation, not in space but in the complex phase of a particle's quantum field. You can't see this symmetry, you can't feel it, but every spark, every light bulb, every heartbeat relies on it. Symmetry becomes law, law becomes constraint, constraint becomes behavior, and behavior becomes reality. Now shift focus to the periodic table. Why do certain elements bond the way they do? Why do noble gases sit inert? Why does oxygen form 2 bonds, nitrogen 3, carbon 4? Because of symmetry in electron arrangements, the balance of filled and unfilled orbitals. Atoms seek the lowest energy configuration that still respects quantum numbers and symmetry. They don't bond randomly, they bond symmetrically. Water, for instance, H2O, is not a straight molecule, it's bent. The lone pairs on oxygen repel the hydrogen atoms, pushing them into a 104.5-degree angle. That shape isn't chemical whimsy. It's spatial symmetry balanced against electron repulsion. Your body is made of molecules shaped by angles that emerged from quantum constraints, shaped by symmetries built into the very structure of the vacuum. It sounds absurd, but it's true. And there's more. Symmetry also explains why particles exist in families, why electrons have heavier cousins, muons and taus, why quarks come in flavors, why force carriers like photons, gluons, and W and Z bosons arise from the symmetries of their respective fields. These particles are not random. They are the byproducts of gauge symmetries, higher-order invariances that govern how forces behave. In other words, symmetry doesn't just sculpt atoms, it sculpts the universe. And yet, symmetry alone is not enough. Because the most dramatic moments in cosmic history, the birth of structure, the ignition of stars, the emergence of complexity, all began when symmetry was broken.
In the next chapter, we'll explore this paradox.
Why would a universe defined by symmetry shatter it? And how does that shattering, this delicate, deliberate breaking, give rise to everything we know? Because if symmetry is nature's algorithm, then broken symmetry is the plot twist that brings it all to life. It seems counterintuitive that a universe governed by rules, strict, elegant, symmetrical, would become so chaotic, so asymmetrical, so alive. We see symmetry everywhere, the paired wings of a bird, the mirrored petals of a flower, the crystalline lattice of salt. But we also see its absence, a crooked tree, a scarred planet, a lopsided galaxy. And in that absence, something changes. Complexity emerges, diversity multiplies, matter becomes more than math. But here's the secret. The universe didn't start broken. It began in perfect symmetry, and then it shattered. At the beginning, and if such a word even applies, the universe was hot, dense, uniform. The same in every direction, in every place. No atoms, no stars, no elements. Just a smooth, seething plasma of pure energy. Indistinguishable, undifferentiated, symmetrical. But that symmetry could not hold. Something broke it, not with violence, but with inevitability. As the universe cooled, it underwent phase transitions. Like water freezing into ice, the fields that governed reality shifted states. And with each shift, symmetry was lost, and structure was born. These transitions were not cosmetic, they were fundamental. Take the electroweak force, a unification of electromagnetism and the weak nuclear force. At high energies, they were one and the same, perfectly symmetrical. But as the universe cooled, that symmetry cracked and the two forces split. Electrons gained their distinct identity. Neutrinos slipped free. The weak force became weak. Then came the Higgs field, a strange, invisible ocean that permeates all space. Before the Higgs turned on, particles had no mass. They were light-speed ghosts, interchangeable, indistinct. But as the universe cooled further, the Higgs field acquired a non-zero value, breaking the symmetry of the vacuum itself. And suddenly, mass existed. The electrons slowed, the quarks condensed. Some particles were frozen into being, others disappeared entirely. Mass was not added, it was revealed by the loss of symmetry. And that's the paradox. The rules that govern matter were forged in a moment when nature stopped following its own rules. Symmetry breaking isn't failure, it's function. It's not chaos, it's creativity. Because when a perfect crystal cracks, it reveals edges, and edges are where new things happen. Let's go deeper. When a symmetry breaks, something is chosen. A direction, a state, a value. In the Higgs field, for instance, the energy landscape had infinite symmetry, like a perfect bowl. Every direction the same. But when the field settled into its lowest energy configuration, it picked a point on the edge. The bowl was still symmetrical, but the solution was not. This is called spontaneous symmetry breaking, a choice made by nature, not in defiance of the code, but within it. And from that single choice, difference was born, up and down, left and right, matter and antimatter, electrons and neutrinos. The universe began to separate itself into categories, into relationships, into tension. And it is from that tension that everything you know arises. Atoms don't exist in a symmetrical world. They exist in a world after symmetry. Why does the proton have more mass than the electron? Why do quarks bind tightly while electrons drift freely? Why do some particles decay and others endure? Because symmetry was broken in just the right ways. Not randomly, but precisely. As if nature wanted complexity. But here's what's truly strange. For all the elegance of symmetry and all the diversity born from breaking it, The universe didn't go all the way. It didn't break everything. It left behind traces, ghostly remnants of the original perfection. In the structure of atoms, in the arrangement of electron orbitals, in the laws of conservation that still hold. It's as if symmetry was shattered, but never fully erased. We live in the ruins of a perfect equation, shattered, but still legible. And in these ruins, patterns continue. Consider chirality, handedness. Many molecules exist in left and right-handed forms. Mirror images, chemically identical yet biologically distinct. Your body prefers one over the other. Amino acids are left-handed, sugars are right-handed. Why? No one knows. But it may be a relic of a symmetry broken billions of years ago, a moment when the universe chose a side. Or look at the imbalance between matter and antimatter. According to symmetry, they should exist in equal amounts. Every particle has a mirror twin, same mass, opposite charge. So when the universe began, it should have created both in equal measure, only for them to annihilate each other. But that didn't happen. Somehow, matter won. By the smallest possible margin, 1 part in a billion, matter outlasted its mirror, just enough to build galaxies, stars, planets. Another broken symmetry, another cosmic decision. And that's the mystery. Why these breaks, why these outcomes, the laws that govern atoms, the quantum numbers, the orbitals, the periodic table, all rely on these ancient cracks in the code. Without symmetry breaking, atoms wouldn't hold their shape, mass wouldn't exist, and reality wouldn't differentiate. So in a strange twist, it is imperfection that gives the universe its form. It is asymmetry that gives you identity. You are not the product of perfection. You are the product of fracture, of laws bent but not broken, of rules flexed but not erased. And in that fragile balance, atoms obey, electrons settle, matter crystallizes. The code didn't vanish, it adapted, and in its adaptation it became more than logic. It became possibility. In the next part of our journey, we'll step back from the fractures and look at the structure they left behind, the periodic table itself. Because if the universe is running on a hidden code, then the periodic table is the first time humanity caught a glimpse of its syntax. At first glance, it looks like a spreadsheet, blocks of color, atomic weights, symbols and numbers, a bland array of chemistry's raw ingredients, the periodic table of elements. But look closer. This is not just a list. It is the first time human beings saw the code. Not guessed, not imagined. Saw. The periodic table is a portrait of obedience. It is the result of countless electrons doing exactly what they are told, constrained by quantum numbers, locked in orbitals, shaped by symmetry and forbidden states. And what we call chemistry is just this structure playing itself out. Let's rewind to the mid-1800s. Mendeleev, the Russian chemist, noticed something strange. When he arranged elements by increasing atomic weight, patterns began to emerge. Certain properties, reactivity, metallic behavior, gas formation, repeated in cycles. But it wasn't just repetition, it was prediction. He saw gaps, left spaces blank, said, "There should be an element here, we just haven't found it yet." And he was right. Decades later, those missing elements were discovered, and each one fit perfectly where the pattern had predicted. Mendeleev didn't know it yet, but he was mapping the behavior of electrons long before quantum mechanics had even been conceived. Today, we know why the table works. It's not empirical, it's not observational, it's logical. The structure of the periodic table emerges directly from the quantum code. Each row, called a period, represents a new shell, a higher principal quantum number, n. Each jump to a new row means electrons are filling a new layer of orbitals, farther from the nucleus, higher in energy, more reactive. Each column, called a group, contains elements with similar electron configurations in their outermost shell. This is why elements in the same group behave similarly, not because they're next to each other, but because they're echoes of the same structure. Let's take the alkali metals. lithium, sodium, potassium, rubidium. They sit in the first column. Each one has a single electron in their outermost s orbital, 2s1, 3s1, 4s1, and so on. That lone electron is weakly held, easily lost, which is why these elements are violently reactive. Toss them in water and they explode with light and heat. It's not alchemy, it's configuration. Now look at the noble gases: helium, neon, argon, krypton.
Each has a full outer shell, perfectly filled orbitals, no hunger, no imbalance. They don't bond because they don't need to.
They are complete, inert, silent. Again, not personality, structure. From left to right across the table, electrons fill orbitals in a precise order: S, then P, then D, then F. This creates the block structure of the table. S block the first two groups, simple, spherical orbitals. P block, 6 columns on the right, the dumbbell-shaped orbitals. D block, the middle 10, the transition metals with complex overlapping electron behavior. F block, the rare earths and actinides, pulled out and placed below like a footnote to the main text. This is not design, this is consequence. The table's structure emerges from the rules of orbital filling, the Aufbau principle, the Hund's rule, the Pauli exclusion principle, and the underlying symmetry of quantum fields, and yet it looks elegant, almost too elegant. The recurring patterns of valence electrons, the way atomic radius shrinks across a period, the way ionization energy spikes at the start of each row, then falls. All of it points to one unsettling truth. The periodic table is not an invention, it's a window into how the universe builds itself, atom by atom, rule by rule. Let's look at a specific example: oxygen, atomic number 8, electron configuration, 1s squared, 2s squared, 2p to the 4th power. That means its second shell, the one used for bonding, has 6 electrons. It wants 8. 2 are missing, so oxygen forms 2 bonds, exactly 2, no more, no less. In water, H2O, oxygen shares electrons with 2 hydrogens. Bond angle, 104.5 degrees. Why not 90? Why not 120? Because the orbitals won't allow it. Lone pairs on oxygen push the bonds into a bent shape. The geometry is quantum determined. You're not drinking water because it's useful. You're drinking water because quantum numbers demanded it. Let's go deeper. Carbon, atomic number 6. Electron configuration, 1s squared, 2s squared, 2p squared. 4 electrons in its valence shell. It can form 4 bonds: straight chains, rings, double bonds, triple bonds, lattices like graphene, branches like DNA. Carbon is versatile not because it's complex, but because it's simple. Its configuration is perfectly balanced for bonding, stable enough to hold, flexible enough to build. Life didn't choose carbon. And it all flows from the table. Every compound, every mineral, every cell, every drug, every protein, every molecule of oxygen in your blood is the result of this table's logic. Because at its heart, the periodic table is not a chemistry tool. It's a periodic manifestation of quantum constraints. It is what happens when the hidden code inside every atom starts to write its own story. But the table also whispers of deeper truths. Why are there only 118 known elements? Why do they stop? Why doesn't the table go on forever? The answer lies in nuclear physics, in the instability of too many protons, the breakdown of balance between nuclear attraction and electrostatic repulsion. Beyond a point, atoms become impossible. Even here, the code enforces limits. And yet, every element we do have, every row, every block, every gap, fits the pattern, predicted, calculated, decoded. This should be more than informative, it should be unsettling, because it means the universe is not improvising, it's compiling. Atoms don't guess how to behave. They run a program, And the periodic table is the user interface, a fragile translation of that alien syntax into something we can read. But make no mistake, the atoms don't care whether we understand. They are not playing by our rules, we are playing by theirs. In the next chapter, we'll step away from structure and return to principle, to the strange, inviolable conservation laws that the universe enforces without exception. Because if the periodic table shows us what matter can become, then conservation laws show us what matter can never do. There are laws in physics that are flexible, conditional, contextual. They bend with scale, with temperature, with time. Then there are the others, the absolutes, the unbreakables. These are the conservation laws, the non-negotiable demands of the universe, unseen but immutable. Ancient contracts written not in ink or fire, but in invariance, the refusal of certain quantities to ever change no matter what unfolds. They are not enforced by any cosmic overseer. They do not require attention or witnesses, they simply are, and if they were violated, even once, the very foundation of existence would crack. Let's start with the one you already know, energy. Energy cannot be created. Energy cannot be destroyed. It can shift, it can spread, it can transform from heat to motion, from light to mass. But the total must always remain the same. It's not a guideline, it's not a suggestion. It's a law. If an electron drops to a lower orbital inside an atom, it releases energy as light. A photon escapes. The atom doesn't lose energy, it merely passes it on. The accounting is perfect, always. This is why atoms glow, why stars shine, why every fire burns exactly as hot as the energy being released from its chemical bonds. Energy is the currency of the universe, and the budget must balance. But energy is only the beginning. Next comes momentum. Linear momentum, the product of mass and motion, is also conserved. In every interaction, every collision, every explosion or decay, the total momentum before must equal the total momentum after. You can't cheat it, not even at the quantum level. Even in the tiniest atomic interaction, momentum is preserved. A particle decays into two others. Their paths and speeds must balance exactly. The invisible math must add up. It's as if the universe refuses to let anything budge without a perfect counterbalance elsewhere. And then there's angular momentum, the rotation of systems. This too is conserved. A spinning electron, a collapsing star, a spinning ice skater, all follow the same law. This is why neutron stars spin at thousands of rotations per second. As the star collapses, its radius shrinks, and the angular velocity must increase to keep the total conserved. Collapse tightens the spiral, but never breaks the rule, because the rule cannot be broken. But perhaps the most mysterious conserved quantity of all is electric charge. We don't know why the electron has a charge of -1, or why the proton has +1. We only know that every interaction, every reaction, every creation or annihilation must preserve the total net charge. You can't conjure charge from nothing. You can't delete it. It's as if charge is a hidden ledger etched into the substrate of space-time, and every atomic move must balance its books. But here's what's strange. These conservation laws aren't just empirical. They're not things we observed and codified. They are consequences of deeper symmetries we can't see. Remember Nother's theorem from part 6. Every conservation law corresponds to a symmetry. Conservation of energy comes from time symmetry, the idea that the laws of physics don't change over time. Conservation of momentum arises from spatial symmetry, the idea that space is the same in every direction. Conservation of angular momentum? That's rotational symmetry. Spin the universe and the rules don't care. Conservation of charge. That comes from an even stranger symmetry, phase invariance in quantum fields, a kind of invisible rotation in an abstract mathematical space. These are not metaphors, they are literal. If time were not symmetric, if physics changed from one moment to the next, energy conservation would vanish. If space weren't homogeneous, if movement in one direction was physically different than another, momentum would collapse. And yet, they hold. Always. Even when the universe was less than a second old, these rules held. Even in the crushing gravity of neutron stars, or the blistering heat of fusion, or the randomness of quantum decay, they still hold. The code has no tolerance for broken contracts, and the atom is bound by these rules. Consider beta decay, a neutron transforming into a proton, an electron, and an antineutrino. It looks simple, but it's a precision act. Charge is conserved, the neutron is neutral, and the proton +1 and electron -1 cancel out. Energy is conserved. The mass difference between neutron and proton becomes the kinetic energy of the outgoing particles. Momentum is conserved. The motion of the escaping particles must add to zero, or more precisely equal the initial motion of the neutron. And angular momentum? Spin, also conserved. The electron has spin 1/2, the antineutrino spin 1/2. Together, they match the original spin of the neutron. This is not coincidence, this is accounting. Atoms are bookkeepers, and the books are balanced down to the last quantum decimal, but conservation laws do more than prevent chaos. They define boundaries. They're why atoms can't collapse, why stars burn steadily, why nuclear reactions yield predictable energy. They are why atoms behave consistently across time and space. An atom of carbon in your body is no different from an atom of carbon in a distant galaxy, not because it's made of the same particles, but because it follows the same rules. And that may be the most remarkable thing of all. The universe doesn't just tolerate order, it enforces it at every scale. From particles to planets, these conservation laws are the rails upon which all reality runs. But there's one place where the rules appear flexible: quantum mechanics. In certain cases, under very specific microscopic conditions, energy and momentum seem to vanish or appear. Particles flicker into and out of existence. Virtual particles exchange force. It looks like the rules are breaking. The conservation laws still apply, within the uncertainty allowed by quantum mechanics. Over tiny time frames and minuscule distances, nature permits fleeting violations, so long as the sum total balances out in the end. Even here, the rules don't fail, they adapt. Because that's what the code does. It's not rigid like stone, it's flexible like steel, and even in its flexibility, it never ever breaks. In the next chapter, we'll explore the places where this flexibility becomes strange, where the code permits the impossible within strict bounds. Because while atoms must obey the rules, they are allowed to do so in ways that make no sense. Welcome to the weird world of quantum behaviors. The universe, we're told, is logical, predictable, obedient to laws, and for the most part, it is. But at the heart of every atom lies a secret. The rules don't always look like rules. Sometimes following the code means behaving in ways that seem impossible. Welcome to the quantum realm, where particles appear to disobey everything while still conforming to the deepest laws of nature. It's not chaos, it's not randomness, it's structured weirdness. Take, for instance, the phenomenon of quantum tunneling. Imagine a marble rolling up a hill. If it doesn't have enough energy, it can't reach the top. It rolls back down. That's classical physics. But electrons don't play by those rules. In the quantum world, a particle can appear on the other side of a barrier it shouldn't be able to cross, not by climbing over it, but by simply being there. This isn't a mistake, it isn't a glitch. It's allowed by the code. Quantum tunneling is written into the equations, a direct consequence of the electron's wave function, which never completely goes to zero, even beyond the forbidden zone. In that forbidden space, the wave function decays, but it doesn't vanish. There's still a tiny probability the particle can emerge on the other side. And sometimes it does. This is not rare. It's how the sun shines. In the sun's core, protons are packed together under immense pressure. But the electrical repulsion between them, their positive charges, is enormous. Classically, they should never fuse. The barrier is too high, and yet fusion happens because of tunneling. The protons don't climb the barrier, they tunnel through it. Stars exist because the quantum code allows particles to bypass the impossible by obeying a different kind of logic.
And it doesn't stop there.
Let's talk about superposition, one of the most misunderstood yet foundational aspects of quantum mechanics. In the classical world, things are one way or another. A coin is heads or tails, a switch is on or off. But in the quantum world, an electron is not here or there, it's both, until you look. This isn't metaphor, it's reality. Quantum particles don't have a single definite state until they're observed. Until then, they exist in a superposition, a blend of all possible states, each with a certain probability amplitude. The famous thought experiment of Schrödinger's cat in Alive and Dead is an attempt to illustrate this absurdity. But inside atoms, it's not thought, it's fact. Electrons don't orbit like planets. They don't trace a path. They exist as probability clouds, not points. Ask where the electron is, and the code doesn't answer with a location. It answers with a range of possibilities. Only when you measure, when you force the system to interact with the outside world, does the wave function collapse. The electron picks a spot. The cat lives or dies. Reality crystallizes. Before that, it's undefined, or more accurately, multiply defined. And yet, through all this, the conservation laws remain intact. The quantum numbers still govern what's allowed. The atom still obeys the code, even if that obedience looks like paradox. It gets weirder. Enter entanglement. When two particles interact in just the right way, their quantum states become linked, not just correlated but entangled. From that point on, measuring one instantly determines the state of the other, even if they're separated by light years. It's not communication, it's connection. Their combined wave function becomes one system, a single equation stretched across space. Einstein called it spooky action at a distance. But again, it's not magic. It's math. The code allows it. In fact, it requires it. Entangled particles still obey all the same conservation laws of spin, of energy, of momentum. But they do so in a way that defies locality. The universe behaves as if space and time don't apply, at least not in the way we're used to. You can split two entangled particles and send them to opposite ends of the galaxy. Measure one, and the other responds, not by signal, but by necessity. This is not science fiction. It has been proven again and again in laboratory experiments. Atoms don't just behave weirdly, they behave weirdly on purpose, because the code says they can. In the strange terrain of quantum mechanics, weirdness isn't an accident. It's a feature. Quantum tunneling, superposition, entanglement, these aren't loopholes. They are how the system works. The code isn't broken. It's just alien. It permits the impossible, within precise bounds. Even uncertainty, the Heisenberg principle, isn't sloppiness, it's law. You cannot know both a particle's position and momentum with absolute certainty. The more precisely you measure one, the less precisely you can know the other. Not because of faulty instruments, because the code prohibits it. There's a limit to what reality will reveal at once. But why? Why would the universe build itself this way? Why allow behaviors that seem to mock cause and effect, space and time, certainty and logic? Maybe it's because, at the smallest scales, information is more fundamental than substance. Atoms don't have position or momentum in the way we imagine. They carry probabilities, potential outcomes, instructions waiting to be read. The code is not a map, it's a script, and until it's performed, its meaning isn't fully realized. And that's the strange truth. The atom follows rules, but the rules are not rules as we understand them. They are permissions, constraints, ghostly instructions that don't dictate what must happen, only what can. And sometimes, what can happen is stranger than anything we dare believe. In the next part, we'll zero in on one of the most bizarre of these ghostly permissions, spin, a property so fundamental to the atom and yet so wildly misunderstood. It challenges the very idea of what motion even is. Because when you think of spin, you're thinking too classically. The truth is far, far weirder. If you hear the word spin, you probably picture motion. A planet rotating on its axis, a ballerina twirling mid-air, a coin spinning on a table before it falls flat. But in the quantum world, spin isn't motion. Not really. And yet, it's one of the most essential rules in the universe. Every electron, every proton, every neutron, every fundamental particle carries spin. And without it, the code collapses. Let's begin with a simple truth. Spin is not spin, not in the classical sense. An electron is not a tiny ball spinning like a globe. It's a point particle with no surface, no edge, no internal structure. There is nothing to rotate. And yet it has angular momentum. Why? Because that's what the math demands. The equations that describe particles, specifically the Dirac equation, which merges quantum mechanics with special relativity, don't just allow spin, they require it. When you solve the equation for the electron, spin emerges naturally, like a hidden variable suddenly snapping into visibility. It's not a choice, it's a consequence. And this spin comes in discrete values, no gradual rotation, no spectrum, just two options, +1/2 and -1/2. We call them up and down, but these are just labels. The spin doesn't literally point up or down unless you choose an axis to measure it by. And even then, it's probabilistic, uncertain until observed. But why does this matter? Because spin does more than add a layer of identity. It defines what a particle is allowed to do. It determines how it moves through a magnetic field, how it aligns with other particles, how it builds atoms, molecules, magnets, and even the stars. Take the Pauli exclusion principle, the law that says no two electrons in an atom can have the same set of quantum numbers. Without spin, this rule wouldn't work. Two electrons could easily occupy the same orbital with the same energy and configuration. The atom would collapse in on itself, no shells, no structure, no chemistry. But with spin, each orbital gets two slots, one spin up, one spin down. This is why helium's two electrons can share the 1s orbital, but lithium's third electron must move up to 2s. This is why elements form in layers, why the periodic table unfolds in cycles. Spin is the tiebreaker, the final digit in the electron's identity. But it's more than bookkeeping. Spin has real physical consequences. Consider the Stern-Gerlach experiment performed in 1922. A beam of silver atoms was passed through a non-uniform magnetic field. Classically, you'd expect the atoms to scatter in a continuous smear, depending on the orientation of their angular momentum. But that's not what happened. Instead, the beam split cleanly into two. Half the atoms deflected upward, half deflected downward. No in-between, no blur. Just two possible outcomes, spin +1/2, spin -1/2. This was the first experimental evidence that spin was quantized, a fundamental binary property baked into the identity of the atom. It shattered classical assumptions and opened the door to a stranger view of reality. Because spin interacts with magnetism. Electrons generate a tiny magnetic moment, not because they move in circles, but because spin itself is magnetic. A single unpaired electron in an atom can make the atom magnetic. A collection of atoms, all with aligned spins, becomes a ferromagnet, like iron. The reason your fridge can hold up a magnet is spin. The reason your brain can form thoughts is spin. Yes, really. Many quantum biologists believe that spin-based processes play a role in biological systems, from avian navigation to enzyme reactions, to the physics of consciousness itself. This is not mysticism, It's chemistry. Spin determines how electrons pair, how orbitals shape, how bonds form. It influences molecular geometry, reactivity, and even the flow of electrons through proteins. In short, spin is not decoration, it is decision. But it gets stranger. Spin isn't just for electrons. All particles have spin, including the ones that mediate forces. Photons, spin 1. Gravitons, if they exist, spin 2. Gluons, spin 1. The Higgs boson, spin 0. The quarks that make up protons and neutrons, spin half. This matters because spin determines statistics, how particles behave in groups. Particles with half-integer spin, 1 half, 3 halves, 5 halves, are called fermions. They follow Fermi-Dirac statistics. They cannot occupy the same quantum state. Electrons are fermions, that's why atoms have structure. Particles with integer spin, 0, 1, 2, are called bosons. They follow Bose-Einstein statistics. They can pile into the same state. Photons are bosons. That's why light beams can pass through each other, overlap, amplify. In fact, under the right conditions, bosons can form a Bose-Einstein condensate, a state of matter where particles lose their individuality and behave as one quantum entity, all because of spin. This invisible, non-spinning spin shapes everything, and yet we can't picture it. It doesn't behave like anything in our macroscopic world. You can't slice it, you can't watch it whirl, you can't slow it down or reverse it. You can only measure its effects, and when you do, it's always there. Perfect, binary, obedient, and it raises a final, unsettling truth. Particles are not objects, they are representations of deeper mathematical symmetries. Spin isn't a thing a particle has. It's what a particle is in relation to the group of transformations it belongs to. This is where physics brushes against philosophy. What are we, if not collections of particles? And if particles are just representations of symmetry, then are we? Are atoms just the visible trace of an invisible code, a shadow cast by mathematics? In the next part, we'll press deeper into this question and look at the eerie reality of particle identity. Why electrons are truly indistinguishable, why atoms don't care which particles they contain, and what it means for you if your body is built from patterns that are repeated everywhere forever. Because spin gives you structure, but identity may be an illusion. You are made of atoms. That much is clear. Oxygen, carbon, hydrogen, nitrogen, trillions upon trillions of atoms arranged into the patterns we call muscles, neurons, bones, breath. But here's the disturbing part. There is nothing, not a mark, not a scratch, not a single subatomic feature that makes your atoms different from anyone else's. Not even a little. The electrons in your brain are identical to those in the heart of a star. The protons in your blood are indistinguishable from the ones in a virus, or a diamond, or a supernova. Not similar, not close enough. Exactly, the same. In physics, this isn't just a philosophical quirk, it's a fundamental fact. Particles of the same type, electrons, photons, quarks, are perfectly identical. There is no serial number, no fingerprint, no tag you can attach. And more importantly, there is no way in principle to tell them apart. You could swap 2 electrons and the universe wouldn't change. It wouldn't even notice. This is not a limitation of our instruments. It's a property of the code. It means that when we write the wave function of 2 electrons, we must write it in a way that doesn't distinguish which is which. Their identities are merged, entangled, blurred into a single inseparable pattern. In other words, particles are not things. They are positions in a pattern, excitations in a field, temporary locations where the universe's deeper symmetries allow matter to appear. You are not made of this electron or that proton. You are made of roles being filled, instructions being executed. Let's make this real. Imagine 2 electrons in an atom, say the 2 in helium's 1s orbital. They have opposite spins, they share the same space, they're locked in the lowest energy state allowed by the Pauli exclusion principle. But which electron is which? The answer is, the question makes no sense. There is no which. You can't mark one, track it, follow it around. Even if they interact, even if they fly apart and come back together, you can't ever say, this is the same one I had before. There is no individuality, just interchangeable code. Now extend this. All electrons in the universe, all of them, are part of the same indistinguishable set. The one in your eye, the one in a lightning bolt, the one in a quasar. They are all copies of the same pattern, flickering into specific configurations depending on what's allowed by quantum numbers and conservation laws. Richard Feynman once joked that maybe all electrons are the same electron, zigzagging through time, appearing in different places. It's not true in any literal sense, but metaphorically, it's disturbingly close, because in quantum field theory, particles are not fundamental. Fields are. The electron is just a ripple, a tiny localized oscillation in the universal electron field. That field spans the entire universe. Every time you have an electron, what you really have is an excitation of that field. That ripple follows rules. It has spin 1/2, negative charge, a specific mass. But the ripple could happen anywhere, anytime, in anyone. This isn't just true of electrons, it's true of all matter. Every proton is an excitation of the quark fields, bound by the gluon field. Every photon is a pulse in the electromagnetic field. Your entire body is a temporary arrangement of field excitations, not a fixed thing, but a constantly shifting pattern sustained by the rules of quantum mechanics. Let that sink in. You are not made of your atoms, you are made of borrowed atoms. For a time, they are arranged in a way that sustains you, your thoughts, your memories, your breath. And then, slowly, inevitably, those atoms leave. They are exhaled, sweated out, exchanged with food, with air, with dust. The atoms in your body are constantly being replaced. Within a year, most of them will be gone, but you remain. Why? Because you are not the atoms, you are the pattern, the shape, the structure of the code. Your brain is not a set of particles. It is an ongoing choreography of particles stepping into and out of a role. Like actors in a play, the cast may change, but the performance continues. This is why identity, at the atomic level, becomes slippery. Matter, it turns out, has no loyalty. Electrons don't belong to anyone, they just follow the rules, fill the available orbitals, obey the exclusion principle, respect conservation laws, and then move on. So what does this mean? It means that reality is not built from things. It is built from possibilities, from arrangements, from slots being filled and emptied, from permissions granted and revoked. You are not the sum of your parts. You are the result of their configuration, a self-sustaining map of allowed behaviors, carved into the fabric of fields. Even death in this light becomes less about destruction and more about dispersal. The pattern fades, the arrangement dissolves, but the particles remain, ready to form something new. And that perhaps is the most unsettling and beautiful truth of all. There is no unique you at the level of matter, but there is a unique arrangement. A fleeting, structured moment when the rules aligned just so, and the code ran you. In the next chapter, we'll explore what happens when these indistinguishable particles, governed by exclusion, shaped by orbitals, defined by spin, begin to link arms and build complexity. Because once the code reaches a certain point, atoms stop being lonely, and chemistry begins to resemble intention. The atom doesn't know it's alive. It doesn't sense, or think, or hope. It doesn't yearn to bond or strive to replicate. It simply follows the code. But that code, strict, mathematical, unemotional, eventually gives rise to something astonishing. Life, not by magic, not by accident, but by obedience. Every breath you take, every cell dividing in your body, every neuron firing in your brain, all of it begins with atoms following rules so rigid, so absolute, they make life possible. Let's begin at the smallest scale, chemical bonding. Atoms bond because their electrons are constrained. Each must fill available orbitals without violating the Pauli exclusion principle. Hydrogen with one electron seeks another to fill its 1s orbital. Oxygen with 6 valence electrons wants 2 more. Nitrogen seeks 3. Carbon with 4 becomes the universal connector. This isn't desire, it's geometry. The configuration of electrons and the rules about which orbitals can be filled and how dictates everything about how atoms interact. In molecules, electrons are shared, transferred, arranged to minimize energy and maximize stability. Water forms because 2 hydrogens complete oxygen's shell. Ammonia forms because nitrogen's 3 unpaired electrons find 3 partners. Methane forms when carbon makes 4 bonds, 1 in each direction of a perfect tetrahedron. And DNA, well, DNA is just chemistry too. Its spiral ladder of nucleotides, adenine, thymine, cytosine, guanine, are molecules assembled from carbon, hydrogen, nitrogen, oxygen, phosphorus. The rungs of the ladder are held together by hydrogen bonds, weak, reversible connections born from the rules of electron configuration. They don't think, they don't care, they just fit. The code doesn't recognize DNA as special. But the patterns it allows, they are capable of encoding information. They are capable of self-replication. They are capable of evolution. This is the bridge between physics and biology. Not a leap, but a slow, inevitable rise in complexity, because the rules don't stop at atoms. They scale, they govern molecules, reactions, interactions. They define which structures are stable, which fold, and which collapse, which persist under heat, under pressure, in water, in acid. They define life, not by intent but by possibility. The structure of proteins, for example, is determined by the precise sequence of amino acids, themselves built from atoms obeying orbital and bonding rules. Each amino acid folds in 3-dimensional space based on steric hindrance, electrostatic attraction, hydrogen bonding, all rooted in electron behavior. Fold the protein wrong, and it's useless. Fold it right, and it becomes a machine. Enzymes, channels, motors, signals all emerge from this architecture of permission. No part of the protein wants to fold. It simply must, according to the rules. And yet, it works. It moves, it acts, it builds. This is what's so haunting. Life is not a violation of the code. It is the fulfillment of it. Not a rebellion against physics, but a precise fractal extension of atomic law. Even the cell, the most basic unit of life, is built from millions of molecules, each held together by constraints, each behaving exactly as the rules permit. Lipid membranes form because hydrophobic tails and hydrophilic heads react differently to water, forcing them into a bilayer. The nucleus holds DNA because charge repulsion and packing density balance perfectly. Mitochondria power the cell through a cascade of electron transfers. Yes, electrons again, flowing through molecules that accept and donate them, all governed by energy levels and orbital compatibility. This isn't animation, this is computation, and it all comes down to atoms filling in the blanks. You are made of carbon, hydrogen, oxygen, nitrogen, phosphorus, sulfur, not because those atoms are rare, but because they are versatile within the code. Carbon bonds in 4 directions, flexible yet stable. Oxygen and nitrogen allow hydrogen bonding, essential for structure and specificity. Phosphorus stores energy in high-energy bonds, like in ATP, the cell's energy currency. Hydrogen provides lightweight bonding. The periodic table didn't suggest these atoms. The rules selected them. Biology didn't invent chemistry, it inherited it. And over time, complexity compounded, not randomly, but through the filtering of stability. The molecules that broke apart didn't survive. The ones that held together, that could copy themselves, that could persist across time and mutation, endured. Evolution is not a competitor to physics. It is a process bounded by physics, a search for stability within the code. And what about thought? Consciousness? The firing of neurons? That too is chemistry. Each neural impulse is an electrochemical wave, ions like sodium and potassium flowing across membranes through carefully gated channels. Those channels are proteins. The proteins are molecules. The molecules are atoms. The atoms are obedient. Every spark of thought, every dream, every whisper of memory, encoded in atoms moving as they must, no more, no less. Not by will, by permission. This doesn't strip life of meaning. It gives it context. It shows that complexity is not a miracle. It's an emergent property of order. The deeper you look, the more miraculous it becomes, not because life defies the rules, but because it arises precisely because of them. We call it life. The universe calls it structure. And beneath it all, the code runs, quiet, unyielding, perfect. In the next chapter, we will ask what happens when the code seems to fail, when decay begins, when randomness intrudes, when the atom structure begins to unravel. Because even in death, the code continues. And sometimes it rewrites the ending. Every system has limits, even one as elegant and absolute as the hidden code inside every atom. For most of the universe, the code holds. It defines the rules, sets the permissions, enforces the constraints. And yet, there are moments when the structure begins to fray, not break, but bend. Atoms decay, bonds rupture, stability slips away. And in those moments, at the edge of obedience, we see what happens when the code fails. But the failure is not chaos, it is structured collapse. Let's begin with one of the most dramatic examples, radioactive decay. Take uranium. Its nucleus is massive, 92 protons, 146 neutrons, a heavy, unstable cluster of matter bound together by the strong nuclear force. But there's a problem. With so many protons in such close quarters, the repulsive force between like charges, electrostatic repulsion, starts to compete with the binding force. The code still applies, but the balance is fragile. Eventually, the structure becomes unstable. The atom must change, and it does, by decaying. Uranium-238, for instance, can undergo alpha decay, ejecting 2 protons and 2 neutrons in the form of a helium nucleus. This reduces the nuclear charge and shifts the element down the periodic table, turning uranium into thorium. It's not random, it's inevitable. The atom obeys the rules by transforming, or take beta decay. Here, a neutron within the nucleus transmutes into a proton, emitting an electron and an antineutrino. Again, the total energy, charge, spin, and momentum are conserved. The code isn't violated, but the identity of the atom changes. Carbon becomes nitrogen, strontium becomes yttrium. The atom evolves. It seems like failure, a nucleus breaking apart, an element losing itself. But it's not failure. It's a return to stability, a correction. The atom, pushed beyond its optimal configuration, seeks a new one. It does not rebel. It adapts. Even half-life, the probabilistic ticking of decay, is not truly random. It emerges from the underlying wave function of the nucleus and the probability of a tunneling event occurring. Yes, quantum tunneling again. That strange permission to cross forbidden boundaries, even in the heart of the atom. Every radioactive particle, when it decays, does so not because it was meant to, but because the probability of it doing so reached critical mass. Like a roulette wheel spun trillions of times, the odds finally catch up. And when they do, the structure changes, a decay, a transmutation, an ending that obeys, even as it unwinds. But failure isn't limited to the nucleus. It happens in molecules too, in mutations. DNA, the storage device of biology, is held together by hydrogen bonds and the positioning of atoms in specific geometries. But those geometries are fragile. A single cosmic ray, a stray high-energy particle from a distant star, can slam into your DNA and knock an electron out of place. One nucleotide misread, one bond broken, one atom shifted, and the code is rewritten. Sometimes the damage is repaired. The molecular machinery of the cell, itself built by the code, kicks in, snipping, patching, copying, editing, but not always. Sometimes the mutation persists. And if it happens in just the wrong place, in a gene that regulates growth or repair or replication, the consequences ripple outward. Cancer, dysfunction, collapse, a failure of structure, of fidelity, and yet it's all within bounds. The atom doesn't break the law when it mutates. It simply follows the new configuration that the disturbance allows. Even aging is a slow accumulation of these atomic failures. Mitochondria leak electrons, proteins misfold, DNA strands fray at their ends. Entropy creeps in, not as a violator but as a permitted decay, a soft erosion of precision, and always the code remains, obedient but fragile, consistent but not eternal. Which brings us to quantum uncertainty. Heisenberg's uncertainty principle tells us that there are limits, fundamental limits, to what can be known about a particle.
Position and momentum.
Energy and time. The more precisely you know one, the less you can know the other. This isn't due to measurement error. It's baked into the fabric of reality. It means that some level of unpredictability is required. A particle may tunnel through a wall, not because it wants to, but because its wave function allows a tiny, non-zero probability. A radioactive atom may decay now, or in 1,000,000 years. The math allows both. This quantum randomness sits beneath everything, even life. Some scientists argue that the firing of neurons may be influenced by quantum effects. That in the tangled web of synapses and ion flows, tiny fluctuations, allowed by the uncertainty principle, could amplify into choices. Could randomness at the atomic level influence free will? We don't know, but we do know this. The code allows for uncertainty. It builds in failure. The atom is not designed for perfection. It is designed for persistence, despite decay. Every structure eventually breaks down. Every configuration ends. But the rules, they remain. Even when atoms decay, when molecules break, when structures collapse, the underlying principles do not blink. Decay does not break the code. It completes it. Entropy, that slow drift into disorder, is not chaos. It is structure, moving toward maximal probability. And perhaps that is the code's final elegance. It permits complexity. It permits order, but it also permits its own unraveling, not as punishment, as closure. In the next chapter, we will step back from these small-scale collapses and look at the cosmic consequences of the atomic code. Because this is not just a set of rules for electrons and orbitals. It is a language that echoes through galaxies. And the same numbers that build hydrogen also build the stars. So far, we've stayed small. Inside the atom, inside orbitals. Inside the quiet spaces where electrons flicker, bonds form, and matter whispers its way into molecules. But now we step back. We widen the frame. Because the same code, the same invisible set of quantum numbers, conservation laws, symmetries, and exclusions that defines the structure of an atom also governs everything above it. The stars, the galaxies, the universe itself. You see, atoms are not separate from the cosmos. They are not passengers. They are not bricks. They are the instructions that make the universe buildable. Let's begin with the simplest atom, hydrogen. One proton, one electron. It was the first thing the universe made. After the Big Bang, as space cooled and expanded, quarks froze into protons and neutrons. Electrons hovered nearby, but the early universe was too hot, too chaotic for them to bind. Then, roughly 380,000 years later, the temperature dropped enough for electrons to settle into orbitals. Hydrogen formed, simple, stable, obedient. And with hydrogen, the code had its first actor, but the story was just beginning. Clouds of hydrogen gathered under gravity, collapsing into enormous searing spheres. Stars, and deep in the cores of those stars, under unimaginable pressure and heat, hydrogen atoms were forced so close that their quantum barriers began to blur. And once again, the code permitted the impossible. Fusion, Protons, like charges, repel each other with incredible force. But quantum tunneling, the same strange permission we saw in decay, allowed some of them to tunnel through their mutual repulsion and get close enough for the strong nuclear force to take over.
2 protons fused,
Then a third.
Hydrogen became helium.
Mass was lost, energy was released, and light, starlight, was born. It all comes from atoms, from the quantum rules that determine energy levels and bonding, symmetry, and spin. Stars burn not through chaos, but through perfect obedience. The periodic table itself, the heavier elements, are born in stars. Inside their cores, helium atoms fuse into carbon, carbon into oxygen, oxygen into silicon, and so on, until iron. But iron marks the boundary.
Fusing iron doesn't release energy, it consumes it.
So when a massive star begins fusing iron, it seals its fate. It collapses. In that collapse, in a final act of gravitational defiance, something extraordinary happens. A supernova. A star dies, explosively. And in that cataclysm, new elements are forged: gold, uranium, cobalt, iodine. Everything heavier than iron, all the atoms that make blood and bones and brains, are built in a single moment of violence. A moment that obeys the same quantum rules as the quiet chemistry of water. The same spin, the same orbital filling, the same exclusions, the same symmetry constraints. The code doesn't break in a supernova. It expresses itself more violently. And when the dust clears, those atoms drift. They float in the void, they gather again, they seed new stars, new planets, new possibilities. And eventually, one quiet afternoon, those atoms find themselves in the blue oceans of a planet called Earth. And some of them form life, and some of that life begins to ask, why? Why does the universe look like this? Why these atoms? Why these stars? Why this code? Because make no mistake, the code does not stop at the atomic level. It scales up. The structure of galaxies, their swirling disks, their collapsing cores, follows from the same rules of conservation. Conservation of angular momentum explains why collapsing clouds spin faster, flattening into rotating disks, the very structure of spiral galaxies. Conservation of energy governs star formation, planetary orbits, black hole accretion. The formation of the universe itself, its expanding fabric, its temperature gradients, its large-scale structure, is imprinted with the fingerprints of the code. Even time bears the weight of the laws. Because energy is conserved only if time is symmetric, and so far it is. The fact that we can observe distant galaxies and predict their paths is a reflection of that unbroken symmetry. And yet, there are limits. The universe expands, entropy grows, stars die, black holes evaporate,
Matter becomes radiation.
Eventually, perhaps the last particles will decay, and only the cold quantum fabric will remain. The rules will still be there, but their expression will be silence.
The code does not require complexity.
It only permits it, for a while, and yet, what a while it has been.
from a handful of hydrogen atoms to a planet teeming with life.
From the blind shuffling of electrons to the emergence of thought, language, curiosity, from spin and symmetry to you. There is something humbling in the realization that the universe doesn't need us to understand it. It simply runs the code. Flawlessly, every atom from every star in every corner of the cosmos follows the same instructions. You, a conscious being made of stardust, are not outside the system. You are the code folded into complexity, and maybe that's enough. In our final chapter, we will turn inward and ask the last question, the question beneath all others, not how the code works, but why it exists at all, because if the universe is running a program, then somewhere, buried in the silence, might be the fingerprints of a programmer. Every atom obeys. It never hesitates, never improvises, never disobeys. The quantum numbers are followed. The exclusion principle is enforced. The conservation laws of energy, momentum, spin, and charge are satisfied without exception. And together these rules construct everything: stars, planets, oceans, cells, thought. The universe doesn't create complexity, it permits it. And what we see, what we are, is what's allowed. But as we reach the end of this journey, one final question remains. A question not of science, but of origin. Who or what wrote the code? Why is the universe governed by math? Why are atoms not arbitrary? Why does nature seem to speak in equations? We've seen how the quantum world runs on a system of rules: quantum numbers, symmetries, conservation laws. We've seen how those rules scale up to form chemistry, biology, consciousness, and cosmos. But none of it explains why the rules are there in the first place. Why should an electron always carry a charge of -1? Why should spin exist at all? Why should no two electrons ever share the same state? Why should energy be conserved? We don't know. We know how. We've written the equations. We can measure, predict, manipulate, but we don't know why the equations take the forms they do. Why nature obeys them so precisely. This is the mystery. Because the universe could have been different. It didn't have to allow atoms to form. It didn't have to stabilize hydrogen or permit fusion. It didn't have to shape the periodic table in elegant repeating patterns. It didn't have to allow for chemistry or life or thought. But it did. And it didn't stumble into this structure blindly. It stitched it together with mathematical precision. Every constant, the charge of the electron, the strength of the strong force, the mass of the Higgs boson, fits into a system that is delicately balanced. Too much change in any direction and the code breaks. Atoms fall apart. Stars never form. Life becomes impossible. This isn't just fine-tuning. It's as if the universe is written in a language, one we are only beginning to decode. Some physicists argue that these laws are inevitable, that they emerge naturally from deeper symmetries or from the structure of the vacuum itself. Perhaps. But even if that's true, we still don't know why those deeper structures exist. We still don't know where the language comes from. Mathematics is not just a tool we invented. It appears to be embedded in the fabric of reality, as if the universe is computing itself. Some go further. They suggest we may be living in a simulation, that reality is not continuous, but quantized, discrete, digital, that the particles and fields we observe are not material, but information being processed. In this view, the universe doesn't exist. It's being rendered, executed, run like a program. If that's true, then the code isn't just like a computer language. It is one. And behind that, a programmer, a designer, an origin. But this is speculation. All we know is that the code is there. It doesn't break, it doesn't age, and it doesn't blink. From the first atom to the last collapsing star, the rules remain unchanged. Even in the deepest randomness, in quantum fluctuations and probabilistic decays, the structure holds. Uncertainty is allowed, but law is never violated. So, what does that mean? Is the code eternal? Was it born with the Big Bang? Did it precede time?
Or is it emergent, a natural result of mathematics unfolding in the only way it can?
We don't know, and maybe we never will. But here's what we do know. You, listening now, are made of atoms, and those atoms are running the code. You are a fleeting expression of perfect obedience, a pattern in motion shaped by exclusion, symmetry, conservation, and permission. You were never outside the rules. You are their consequence. You are their voice. And somehow, against all odds, the atoms arranged themselves into a being that could ask the question, why? Why this code? Why this universe? Why me? And though the code does not answer, it allows the question to be asked. That may be its final elegance, that in a cold mathematical universe. The rules gave rise to wonder, and in that wonder, perhaps, we glimpse something greater than atoms. Something that whispers, not what the code says, but why it was written. Thank you for joining us on this extraordinary journey through the universe here on Frontiers of Infinity. If this glimpse into the unknown has sparked your curiosity, be sure to subscribe and join us. where we unravel the darkest mysteries of space.